Welcome all. I, Yash Firke and Prashant Kumar will be presenting our work on the CFD code optimization using Coupa and CUDA. This is a course project for high performance computing and its application. Course instructor Mahendra Verma. We will first see the Coupa code Dhara developed by Harshit Tiwari. It is an inviscid compressible Navier-Stokes solver, and the equation for the solver is given as the conserved variables and the flux variables for x and z directions are given as follows. Now we will see the code structure for the Dhara. Para file takes in the inputs like the time steps and the number of time iterations, the grid size, etc. Then the field variables are initialized using the initial condition in init fields. The grid file generates the grid file with equal dx and dz uh, ta- equal dx and dz steps in a structured form. The boundary file imposes the boundary conditions like periodic boundary conditions and the Neumann and Dirichlet boundary conditions depending upon the problem statement that we are trying to simulate. The derivative file finds these second order central difference derivatives of the fluxes in each direction. The compressible file is where the fluxes are calculated for x and z direction, and the derivatives are called in this file. The all these files are imported in FNS file, which runs our time steps where the conserved variables are updated and the fluxes are calculated, and the printing and the saving are also carried in this step subsequently. The main file is the one that we run all our is the one that where the initialization of the program takes place and the iteration starts. The Euler time step is the most time consuming portion of the code, which we will be seeing its optimizations.
So we have as initial condition we have constant density, and we have a step function in the x direction for x velocity as well as z velocity, and we can see that the density is propagating in the x direction as well as x velocity is also propagating in the x direction, but velocity is not propagating in the z direction because we have given the constant property in the z direction as initial condition. Now we have changed the initial condition for the z velocity, and we have also given a step function in the z direction, and we can also see that in the z velocity is also propagating in the z direction as well.
Before doing the optimizations, we will be checking the profile of our code. The code is profiled using NVTX markers, which are imported using the Python library. These NVTX, the code is run using the NVTX marker and which generates an output file that can be viewed on the NSAT systems. And this is the timeline of our code as such. Here you can clearly see that the time advancing scheme is initiated on CPU, and on GPU the fluxes values are computed and their derivatives are calculated for x direction. Similar step is carried for the z direction, and then they are updated. The primitive variables are updated later on. After this step, the outputs are printed on the screen for checking their convergence. The output that we are calculating is the total mass, kinetic energy, and internal energy, which is calculated using Simpson 1D and 2D schemes. The maximum Mach number is also printed on the screen. You can clearly see that the printing takes almost significant time compared to the time advance step, and this is unnecessary wastage of our computation time. So our first progress will be commenting out these print statements. This gives us first speed up of 1.75 times against the old code. We also need to comment out our field saving operations, because they also take quite a lot of time, instead of where there is no computation happening, and the field saving is done on the CPU. For checking our computation execution times, we need to omit out these saving timings. So after commenting these save fields, we get at 2.28 times speed up against the previous version. Here you can clearly see that now the time advancing scheme is running after one another without any wastage of printing or saving timings. Now we check our performance against CPU of this code by commenting out the NVTX markers. Here we use the GPU A100 card to run our code for 100 time iterations. The CPU versus GPU speedups are calculated for varying grid size from 128 square to 8000 square, and the red line shows the speed up graph, and the blue dotted line shows the memory usage for running each grid sizes. We can see as the grid sizes increases, the memory also increases along with it, while the speed up saturates after 2000 square grid size. This can be reasoned that our GPU utility reaches almost 100% following 2000 grid, and we have a we have a saturation after that for its speed up timings, for its speed up readings. Now we check the GPU speedups relative to the grid size that we are running. Here 128 cross 128 grid is taken as our reference, whose speedup is taken as 1, and the later on and for the later grids, the speedup is calculated as example for the 256 one is, as we can see, that time is almost similar, but the grid is increased by 4 times. So that means with respect to each grid point, our speed up is almost 4. We taking this into consideration, we calculate the speed up for other grids, and get our speed up curve shown in the red line. And here we also see that for 2000 square grid, we get a saturation where the GPU utility is reached almost 100%.
Further optimization can't be done on the CuPy because it is built on Python library and it does not provide enough control. So we are using CUDA here to solve a 2D Burger equation that contains the temporal term, 2 convective term, and then 2 diffusive term. So we are using the finite difference to solve this. So the convective term is solved as a forward in space, and the diffusive term is used as a central differencing. So we are using the grid here, means the CUDA grid that contains of blocks, and each block has a 16 by 16 threads. So you can see that we are using the 2D grid as a 1D array to solve the equation and get the updated field of u and v, and we are using the periodic boundary condition, and for checking the performance of the code, we are using the 1000 steps of time to get the performance. We are giving the step function in the x direction for the u velocity, and we are giving the step function in the y direction for the v velocity, and we can see that the u velocity is diffusing in the x direction, and the boundary condition is satisfied, the periodic boundary condition, and exactly the same thing is happening for the v velocity, and it is diffusing in the y direction, and the boundary condition is satisfied as well. Now we will see the code performance on the CUDA. We have done the performance check for 2049 cross 2049 grid size for 1000 iteration, and we have seen the CUDA performance is 0.5 second, and the CPU performance is 122 second, and we have seen the speed of 222x. For the InVisit compressible Navier-Stokes CuPy gives 112 speed up, and which is very comparable with the CUDA code. But using profiling and better kernel optimization, we can get the better speed up in the CUDA code performance.